At its most basic level, every computer program functions as a sequence of instructions. These instructions move through a specific flow, taking in data as input, processing it through simple logic gates like AND, OR, and NOT, storing it in memory, and finally producing an output. When you run a web browser, a music player, and a virus scanner at once, it feels like the computer is doing all of that at the exact same moment. But it isn't. The Central Processing Unit or CPU operates like a small team of highly intelligent managers. Instead of performing every task at once, they rapidly switch their attention between them, jumping from the browser to the music to the scanner so fast that it creates the illusion of simultaneous action. Traditional computing relies on this hyper-fast sequential coordination. As software became more demanding, hardware engineers tried to increase speed by adding more managers to the processor, creating multi-core CPUs. However, doubling the number of cores does not automatically double the speed of the software. This diagram illustrates the core problem. Multi-core programming requires dividing instructions perfectly. If two cores attempt to access the same piece of shared memory at the same time, the system hits a bottleneck, visualized here as a collision in the data path. If the tasks fall out of sync, the system can enter a deadlock, a state where different processes freeze because each is waiting for the other to finish. This leads to crashes and significant software errors. Dividing thousands of tasks and safely combining the results without conflict is one of the most difficult challenges in modern programming. While CPU architecture is effective for intelligent control, its sequential design cannot scale to the massive simultaneous requirements needed to simulate reality. The pressure to move past the sequential model came from video games, specifically the mathematical demand of rendering 3D graphics. To draw a digital world, a computer must calculate the lighting, position, and color of millions of individual pixels and geometric vertices at the exact same moment. A small team of CPU managers, no matter how fast they switch tasks, cannot process millions of pixels quickly enough to maintain a smooth visual experience. This gap in hardware led to the development of the Graphics Processing Unit or GPU. This side-by-side comparison shows the architectural shift where a CPU has a few powerful cores for complex logic. A GPU is an army of thousands of smaller, simpler cores. These are designed for massive parallel repetition, performing the same operation across a huge dataset simultaneously. The GPU shifted hardware design away from complex sequential logic towards massive parallel repetition. Directing thousands of parallel cores is significantly more complex than standard programming. It requires a different way of thinking about how data moves through a machine. Developers using a GPU directly must manually manage memory transfers and keep thousands of independent threads synchronized, creating a massive barrier for most creators. Game engines serve as the essential bridge across this complexity. Programs like Blender are used to sculpt 3D assets, while engines like Unity are used to execute them in real time. Unity acts as an abstraction layer. It allows a developer to write human-readable logic for how an object should behave, while the engine handles the translation into the complex parallel execution the GPU requires. By hiding the complexity of low-level hardware, game engines allow creators to wield immense parallel computing power through an understandable workflow. This brings us to a significant twist in computing history. The hardware built to run video games turned out to be the exact requirement for modern artificial intelligence. Training a machine learning model involves calculating massive matrices and tensors. A tensor is simply a multi-dimensional array of numbers that AI uses to process complex data. As shown here, the math is identical. Calculating the value in an A matrix uses the same structural grid as rendering a 3D pixel or simulating physical geometry because the mathematical needs are the same. The GPU, originally custom built for games, became the primary engine for AI. The AI revolution could not have happened without the hardware architecture forced into existence by the demand for better graphics. The road from visual graphics to artificial intelligence runs directly through parallel computing. This historical connection changes how we view education and the tools used by modern creators. Building in tools like Unity and Blender provides direct hands-on experience with the parallel architecture used in advanced industry. These platforms allow for the creation of digital twins, virtual replicas of physical systems that simulate real-world physics and data in real time. Mastering a game engine means mastering the parallel blueprint of the AI era, providing the foundation for the massive simulations that will drive the next generation of technology.